You know what's wild? We've been staring at Jupiter for literally thousands of years. Ancient civilizations tracked it across the night sky. Astronomers mapped its movements with primitive telescopes, and we've sent spacecraft hurtling through the solar system just to get a closer look. And yet after all that time, after all those observations, after all the billions of dollars poured into space exploration, Jupiter just casually dropped a bombshell on us that nobody saw coming. Not the scientists at NASA, not the astrophysicists running complex simulations, not even the most imaginative science fiction writers. Jupiter, that massive ball of swirling gas we thought we had mostly figured out, was hiding something absolutely extraordinary in its depths. Now, before we dive into what NASA actually found, we need to talk about why Jupiter matters so much in the first place. Because this isn't just about one cool discovery on some distant planet. Jupiter is like the neighborhood giant that influences everything around it. It's so massive that it doesn't actually orbit the Sun in the traditional sense. Instead, both Jupiter and the Sun orbit around a common center of gravity that sits just above the Sun's surface. Think about that for a second. Jupiter is so unbelievably huge that it makes the Sun wobble. That's the kind of cosmic heavyweight we're dealing with here. The planet has been our protector for billions of years, and most people don't even realize it. Jupiter's immense gravitational pull acts like a cosmic vacuum cleaner, sweeping up asteroids and comets that might otherwise crash into Earth. Without Jupiter sitting out there in the outer solar system, life on Earth might never have had the stable conditions it needed to evolve. We owe our very existence, at least in part, to this gas giant doing its gravitational bodyguard routine for the past 4.5 billion years. But here's where things get really interesting. Despite Jupiter being so important, despite us studying it for so long, we really didn't know what was going on inside the planet. Sure, we could observe the surface, watch those mesmerizing cloud bands rotate at different speeds, track the Great Red Spot as it raged for centuries. But what was actually happening beneath those cloud tops? That was a mystery wrapped in an enigma, shrouded in layers of hydrogen and helium so dense that even our best instruments couldn't penetrate them. Jupiter kept its secrets well hidden, buried under pressures so extreme that they would crush any probe we tried to send down there. Scientists had theories, of course. They always do. The prevailing idea was that Jupiter was basically a failed star, a ball of gas that never quite got massive enough to ignite nuclear fusion in its core. They figured it was mostly hydrogen and helium all the way down, maybe with a small rocky core at the center, but nothing too surprising. Just a lot of gas under a lot of pressure, gradually getting denser and hotter as you descended toward the center. Simple enough, right? Wrong. NASA's Juno spacecraft changed everything. When Juno arrived at Jupiter in 2016, it wasn't just another flyby mission, snapping a few pictures before heading off into deep space. This was a dedicated orbiter designed to study Jupiter in unprecedented detail, with instruments specifically built to peer beneath those cloud tops and finally answer the question that had bugged scientists for decades. What's really inside Jupiter? Juno's orbit was deliberately designed to be extremely elliptical, swinging in close to Jupiter's cloud tops before rocketing back out to safer distances. This wasn't just for dramatic effect. Jupiter's radiation environment is absolutely brutal. The planet's powerful magnetic field traps charged particles, creating radiation belts that make Earth's Van Allen belts look like a gentle breeze. Electronics get fried, sensors go haywire. Even with extensive shielding, Juno could only spend limited time in close proximity to the planet before the radiation would start causing serious damage. But during those close passes, oh boy, did Juno deliver. The spacecraft carried a gravity science instrument that could detect tiny variations in Jupiter's gravitational field with extraordinary precision. By tracking these minute changes in gravity, as Juno zipped past different parts of the planet, scientists could essentially create a map of what was inside. Different densities, different compositions, different structures, all revealed through their subtle gravitational signatures. And that's when they found it. The thing nobody expected. The discovery that made scientists literally go back and check their instruments multiple times because they couldn't believe what they were seeing. Jupiter has weather. Not just surface weather, but deep, deep weather. We're talking about massive atmospheric phenomena that extend thousands of miles down into the planet's interior, far deeper than anyone thought possible. These aren't just shallow storms confined to the cloud tops. These are colossal structures of rising and falling gas that reach down into zones where the pressure is millions of times greater than Earth's atmosphere at sea level. Now, you might be thinking, okay, that's kind of cool, but is it really that surprising? Jupiter's famous for its storms. We've known about the Great Red Spot for centuries. But here's what makes this discovery so absolutely mind-blowing. These deep weather systems shouldn't exist according to everything we thought we knew about planetary physics. On Earth, weather is confined to the troposphere, the lowest layer of our atmosphere. That's because weather is driven by solar heating from above, and that energy can only penetrate so far down before it dissipates. Earth's weather is essentially a shallow skin phenomenon, limited to the bottom few miles of atmosphere. Scientists assumed Jupiter would work the same way, just on a larger scale. Sure, Jupiter's atmosphere is deeper, but eventually you'd hit a point where the pressure and density would smooth everything out into uniform layers, right? Nope. Jupiter apparently didn't read the textbook. These weather systems just keep going down and down and down. We're talking about depth ranges of 2,000 miles or more. To put that in perspective, that's roughly equivalent to the distance from New York to Los Angeles. Except instead of driving across a continent, you're plunging through layers of hydrogen gas being compressed into exotic states of matter that don't even exist naturally on Earth. The implications of this discovery started a chain reaction of revelations that fundamentally changed our understanding of not just Jupiter, but gas giant planets throughout the universe. Because if Jupiter's weather extends that deep, it means the planet's interior is way more dynamic than we thought. It means there's intense mixing happening between different layers. It means the traditional model of gas giants, as these stratified, relatively stable spheres of gas, needs to be completely rewritten. But wait, it gets even better. Or weirder. Depending on your perspective. As Juno continued its mission, mapping Jupiter's gravity field with increasing precision, another anomaly popped up. The planet's core, that dense, rocky center that was supposed to be sitting peacefully at the heart of all that gas, wasn't behaving the way it should. In fact, scientists started to realize that Jupiter's core might not even be a discrete object at all. The data suggested something far stranger. Instead of a solid, rocky core, Jupiter might have what scientists started calling a fuzzy or diluted core. Imagine taking a traditional planetary core and then somehow spreading it out, mixing it with the surrounding hydrogen and helium until you have this weird gradient region where there's no clear boundary between core and atmosphere. The rocky material is still there, but it's diffused throughout a much larger volume, creating this bizarre transitional zone that defies easy categorization. How did this happen? The leading theory involves a cataclysmic collision early in Jupiter's history. We're talking about the chaotic days of the early solar system, when planets were still forming and massive objects were crashing into each other with apocalyptic force. Something big, probably another protoplanet with several times Earth's mass, might have slammed into Jupiter with such tremendous energy that it literally disrupted the planet's core, breaking it up and mixing it throughout the interior. Think about that for a moment. Jupiter, the biggest planet in our solar system, got hit so hard that its core shattered and dispersed. The amount of energy involved in such a collision is almost incomprehensible. We're talking about an impact that would make the asteroid that killed the dinosaurs look like a firecracker. And this happened while Jupiter was still young, still forming, still gathering mass from the protoplanetary disk surrounding the infant Sunday. This discovery opened up a whole new chapter in planetary science. If Jupiter experienced such a violent collision, what about the other gas giants? Did Saturn, Uranus, and Neptune go through similar traumatic events? And what about exoplanets, the thousands of planets we've discovered orbiting other stars? The universe suddenly seemed a lot more violent and chaotic than our nice, orderly models had suggested. But Juno wasn't done surprising us. Not even close. The spacecraft's microwave radiometer, an instrument designed to probe beneath Jupiter's visible cloud layers, started detecting something absolutely fascinating in the polar regions. You see, Jupiter's poles are very different from its equator. While the equatorial regions are dominated by those famous horizontal bands of clouds racing around the planet at different speeds, The poles are a chaotic swirl of cyclonic storms arranged in bizarre geometric patterns. At Jupiter's North Pole, there's a central cyclone surrounded by 8 other cyclones, all locked in this strange orbital dance around the central vortex. Each of these cyclones is roughly the size of Earth, by the way. We're not talking about little weather systems here. These are planet-sized storms, each one powerful enough to tear our entire world apart, and they're just casually spinning around Jupiter's pole in this weirdly stable configuration. At the South Pole, there's a similar arrangement, but with 5 cyclones surrounding the central storm instead of 8. Why the difference? Nobody knows. What force is keeping these storms in such stable positions, when by all rights, they should either merge together or fly apart? Nobody knows that either. Jupiter apparently decided to create these massive atmospheric structures following rules we haven't figured out yet. The deeper Juno looked, the more questions arose. The microwave data revealed that these polar cyclones extend deep into Jupiter's atmosphere, just like the equatorial weather systems. They're not shallow features painted on the cloud tops. They're 3-dimensional structures with roots that plunge thousands of miles down into the planet's interior. The storms are stacked, with different wind patterns at different depths, all somehow coordinating to maintain these massive vortices. And here's something that really baked scientists' minds. These storms are warm, warmer than the surrounding atmosphere. That means they're being heated from below, from Jupiter's interior. The planet is releasing heat, primordial heat left over from its formation billions of years ago. And that heat is driving these polar cyclones. Jupiter isn't just a cold ball of gas floating in space. It's an active, dynamic world with its own internal heat source. And that heat is powering weather systems that dwarf anything we have on Earth. The more data Juno collected, the more scientists realized they were dealing with a planet that operated on principles far more complex than anyone had imagined. Jupiter wasn't just big Earth with more gas. It was an entirely different category of world, with physics and dynamics that pushed the boundaries of what we thought we understood about planetary science. One of the most startling revelations came from studying Jupiter's magnetic field. Now, we knew Jupiter had a magnetic field. We'd known that since the 1970s, when the Pioneer and Voyager spacecraft flew past and detected it. We knew it was strong, roughly 20,000 times more powerful than Earth's magnetic field. But what we didn't know, what we couldn't have known until Juno arrived, was just how bizarre and complex that magnetic field actually is. Earth's magnetic field is relatively simple. It's what scientists call a dipole field. Basically, like a giant bar magnet buried inside the planet with field lines extending from the North Pole to the South Pole. Sure, it wobbles a bit, and the poles occasionally flip, but the overall structure is pretty straightforward. Jupiter's magnetic field, on the other hand, is absolutely bonkers. Juno's magnetometer mapped Jupiter's field in unprecedented detail, and the results were shocking. The field isn't symmetric like Earth's. Instead, it's lopsided, stronger in the northern hemisphere than in the southern hemisphere. And it's not just a simple dipole. There are multiple magnetic poles, regions where the field strength varies dramatically, and a weird concentrated patch of magnetic field near the equator that scientists dubbed the Great Blue Spot. No, not related to the Great Red Spot. Completely different phenomenon. Jupiter apparently likes to theme its anomalies by color. This Great Blue Spot is a region where Jupiter's magnetic field is particularly intense and reaches deeper into the planet than anywhere else. It's been drifting westward over time, moving at about 2 centimeters per second relative to the rest of the planet's magnetic field. That might not sound like much, but over the decades since we started tracking it, the Great Blue Spot has traveled thousands of miles across Jupiter's surface. What's causing this magnetic weirdness? The answer lies in how Jupiter generates its magnetic field in the first place, and this is where things get truly exotic. Deep inside Jupiter, maybe 15,000 miles down, the pressure becomes so extreme that hydrogen stops behaving like a normal gas. It gets compressed into something called metallic hydrogen, a state of matter that doesn't exist anywhere on Earth naturally. In this metallic state, hydrogen's electrons are squeezed free from their atoms and can move around freely, just like electrons in a metal wire. This creates a layer of electrically conductive fluid surrounding Jupiter's core. or what's left of it after that ancient collision we talked about. As Jupiter rotates, this metallic hydrogen layer rotates with it, and the movement of all those free electrons generates electric currents. Those currents, in turn, create Jupiter's powerful magnetic field through a process called the dynamo effect. But here's where Jupiter's disrupted core comes into play. Remember how we said the core might be fuzzy and diluted? Well, that means the metallic hydrogen layer isn't uniform. There are variations in density, temperature, and composition as you move through it. Rocky material from the disrupted core is mixed throughout, creating irregularities in the fluid's properties. These irregularities affect how the dynamo operates, creating that asymmetric, multipole magnetic field that Juno detected. It's like Jupiter's ancient collision left a permanent scar, not just in its core structure, but in the very magnetic field the planet generates. Every time you observe Jupiter's lopsided magnetism, you're seeing the lingering effects of a cataclysmic impact that happened over 4 billion years ago. The planet remembers. Now, while Juno was busy revolutionizing our understanding of Jupiter's interior and magnetic field, it was also capturing some of the most breathtaking images of the planet ever taken. The spacecraft carried a camera called Juno, which wasn't even part of the original scientific payload. It was added specifically for public engagement, a way to share the beauty of Jupiter with people back on Earth. But Juno ended up contributing to science in ways nobody anticipated. The images revealed Jupiter's atmosphere in stunning, terrifying detail. The cloud tops aren't smooth. They're roiling, turbulent, filled with eddies and vortices and swirling patterns that shift and change constantly. There are massive storms the size of Earth's continents, just casually spinning away in Jupiter's southern hemisphere. There are wave patterns where different atmospheric streams collide, creating standing features that persist for months or years before eventually dissipating. The colors are incredible too. Brilliant whites, deep reds, rich browns, and everything in between. These aren't false colors added by scientists to make the images look pretty. These are Jupiter's actual hues, the result of complex chemistry happening in the planet's clouds. The white zones are areas of rising gas, where ammonia ice crystals form high in the atmosphere. The darker belts are regions of descending gas, where you can see deeper into the atmosphere where different chemical compounds create those brownish tones. And those reds? Those gorgeous crimson and orange hues in the Great Red Spot and other storms? Scientists think they might be caused by organic compounds, complex molecules containing carbon that get created when sunlight breaks apart simpler chemicals in Jupiter's upper atmosphere. The intense radiation environment might also play a role, energizing molecules and causing chemical reactions that produce colored compounds. Jupiter is essentially a giant chemistry lab, running experiments on a planetary scale. But here's something that really got scientists excited. Juno images revealed atmospheric features that changed on surprisingly short timescales. Storms would appear, evolve, and disappear over the course of weeks or even days. Cloud patterns would shift and transform. New vortices would spin up in the turbulent regions where different wind streams met. Jupiter's atmosphere wasn't just dynamic in the sense of having persistent features like the Great Red Spot. The whole system was constantly active, constantly changing, constantly reshaping itself. This raised a fascinating question. What powers all this activity? We've already talked about Jupiter's internal heat, that leftover warmth from the planet's formation. But there's more to the story. Jupiter also receives energy from the sun, just like Earth does. However, here's the kicker. Jupiter actually radiates more energy into space than it receives from the Sunday. The planet is literally glowing with its own internal heat, slowly cooling down over billions of years as it releases the energy it accumulated during formation. This internal heat source is crucial for understanding Jupiter's weather. It means the planet's atmospheric circulation is driven from below as well as from above. Heat rising from the interior creates convection currents, massive overturning motions in the atmosphere that drive wind patterns and storm formation. Combined with the energy from sunlight and the effects of Jupiter's rapid rotation, you get this incredibly complex, multi-layered weather system that extends from the cloud tops down into those mysterious depths that Juno revealed. Speaking of rotation, Jupiter spins fast, really fast. Despite being over 11 times wider than Earth, Jupiter completes a full rotation in less than 10 hours. This breakneck spin rate has profound effects on the planet's atmosphere. It creates the banded structure we see, with different latitude zones rotating at different speeds. It generates powerful jet streams, rivers of fast-moving air that race around the planet at hundreds of miles per hour. And it contributes to the formation of those polar cyclones, spinning them up through a process similar to how Earth's rotation creates hurricanes. But the rapid rotation also creates something else. Jupiter bulges. The planet isn't perfectly spherical. The centrifugal force from spinning so fast causes the equator to bulge outward while the poles are flattened. Jupiter's equatorial diameter is about 6,000 miles larger than its polar diameter. If you could somehow stop Jupiter from spinning, it would gradually relax into a more spherical shape, though the process would take an extraordinarily long time given the planet's immense mass and the viscosity of its interior. Juno's gravity measurements allowed scientists to quantify this bulge with unprecedented precision, and in doing so, they learned even more about what's happening inside the planet. The exact amount of bulging depends on how mass is distributed throughout Jupiter's interior. A planet with all its mass concentrated in a dense core would bulge differently than one with mass spread out more evenly. By measuring the bulge, scientists could infer details about Jupiter's internal structure, adding yet another piece to the puzzle. All of these discoveries, from the deep weather systems to the disrupted core to the complex magnetic field, forced scientists to completely rethink their models of how gas giants form and evolve. The old picture of Jupiter, as a simple, stratified ball of gas, was dead. In its place emerged a portrait of a dynamic, violent, complex world where different physical processes interact in ways we're still struggling to fully understand. And this had implications far beyond just understanding one planet in our solar system. Remember, we've discovered thousands of exoplanets orbiting other stars, and a significant fraction of them are gas giants, similar to Jupiter. Some are even more massive. Some orbit much closer to their stars. Some exist in multi-planet systems, where gravitational interactions create additional complexity. Every one of those distant worlds is potentially just as weird and wonderful as Jupiter, with its own unique history, its own internal structure, its own atmospheric dynamics. The discoveries from Juno gave scientists new tools and new frameworks for understanding these exoplanets. When we detect a gas giant orbiting another star, we can't send a spacecraft there to study it up close. We can only observe it from a distance, measuring how it affects its parent star's light or how its gravity tugs on other objects in the system. But by understanding Jupiter in such intimate detail, we gain insights into what might be happening in those distant systems. Jupiter becomes our Rosetta Stone for decoding gas giants throughout the universe. But let's get back to what Juno found, because we're not done yet. Not by a long shot. One of the mission's instruments, a microwave radiometer designed to peer beneath Jupiter's cloud tops, started detecting something unusual in the planet's atmospheric composition. Jupiter's atmosphere is mostly hydrogen and helium, about 90% hydrogen and 10% helium by mass, with trace amounts of other elements like methane, ammonia, and water. At least, that's what we thought. The microwave data revealed that ammonia, which we'd always assumed was well mixed throughout Jupiter's atmosphere, actually has a much more complex distribution than expected. In some regions, there's way more ammonia than predicted. In other areas, there's significantly less, and these variations aren't random. They correlate with the weather patterns, with the jet streams, with those deep atmospheric structures that Juno had already discovered. What's happening is that Jupiter's vigorous atmospheric circulation is creating chemical segregation. Rising columns of gas carry ammonia upward from deep in the atmosphere, concentrating it in certain regions. Descending columns deplete ammonia from other areas. The jet streams create barriers that prevent mixing, maintaining these chemical differences over long periods. It's like Jupiter's atmosphere has different chemical zones, each with its own unique composition, all maintained by the planet's complex weather patterns. This was another surprise, another deviation from the simple models. Scientists had assumed that Jupiter's powerful winds would mix everything together relatively quickly, creating a uniform composition at any given altitude. But nature, as usual, turned out to be more interesting than our assumptions. The atmosphere wasn't well mixed. It was structured, layered, with chemical gradients that told stories about circulation patterns and atmospheric dynamics. And then there was the water question. Water on Jupiter doesn't exist as liquid oceans or ice caps like on Earth. The temperature and pressure conditions are all wrong for that. Instead, water exists as vapor in the atmosphere, mixed in with all the hydrogen and helium and other gases. But how much water is there? That question turned out to be surprisingly difficult to answer, and it had implications for understanding how Jupiter formed. The amount of water in Jupiter's atmosphere is intimately connected to where and how the planet formed. You see, in the early solar system, there was a temperature gradient in the protoplanetary disk. Close to the young sun, it was hot, too hot for water ice to exist. But farther out, beyond a boundary scientists call the frost line or snow line, it was cold enough for water to freeze into ice. This ice could stick together, accumulating into larger and larger bodies that eventually became the cores of giant planets. If Jupiter formed beyond the frost line, where water ice was abundant, it should have incorporated a lot of water during its formation. If it formed closer to the sun and later migrated outward, it might have less water. The exact amount of water in Jupiter's atmosphere is like a fossil record, a clue about where the planet originated billions of years ago. But measuring water content on Jupiter is maddeningly difficult. Water vapor doesn't distribute evenly throughout the atmosphere. It clumps, it concentrates in certain regions, it gets carried up and down by convection currents. Early measurements from previous missions like Galileo, which dropped a probe into Jupiter's atmosphere back in the 90s, gave confusing results. The probe measured much less water than expected, but scientists suspected it had just gotten unlucky, descending through an unusually dry region. Juno approached the problem differently. Instead of sampling one spot, it measured water across large swaths of the planet using its microwave radiometer. Over time, as the spacecraft completed orbit after orbit, building up a comprehensive dataset, patterns began to emerge. And what those patterns revealed was absolutely fascinating. Jupiter has a lot more water than the Galileo probe suggested. Deep in the atmosphere, in those regions below the clouds where Juno's instruments could peer, water vapor concentrations are several times higher than what we see in the Sunday. This is significant because the Sun's composition represents the baseline, the primordial mix of elements that existed in the solar nebula when the planets were forming. If Jupiter has more water than the Sun, it means the planet incorporated water ice during its formation, supporting the idea that it formed beyond the frost line. But the water distribution is weird. It's not uniform. There are pockets of enhanced water vapor, regions where convection currents have brought water up from deeper levels. There are dry zones where descending gas has depleted water from the local atmosphere. The whole planet is this patchwork of different conditions, different compositions, all driven by that relentless atmospheric circulation. And here's where things get really speculative and exciting. Some scientists think that deep inside Jupiter, where pressures reach millions of atmospheres and temperatures soar to tens of thousands of degrees, something extraordinary might be happening. At those extreme conditions, methane molecules might break apart, and the carbon atoms could get compressed so intensely that they form diamonds. Not little diamonds, massive diamonds, possibly as large as a centimeter across, or even bigger, raining down through Jupiter's interior, like a bizarre precipitation event. It sounds like science fiction, but the physics actually checks out. Laboratory experiments have shown that under the right pressure and temperature conditions, carbon does indeed form diamond structures. And Jupiter's interior definitely has the right conditions in certain regions. So there might be literal diamond rain falling through the depths of the planet, settling down toward the core region, accumulating over billions of years into layers of compressed carbon. We can't prove this yet. We can't send a probe down there to scoop up a diamond and bring it back. The pressures would crush any spacecraft long before it reached those depths. But the theory is consistent with what we know about Jupiter's interior conditions. And it's one of those ideas that perfectly captures how alien and wonderful gas giant planets really are. These aren't just big balls of gas. They're exotic laboratories where matter behaves in ways that push the boundaries of what's possible. Juno also revolutionized our understanding of Jupiter's auroras. You're probably familiar with Earth's auroras, the northern and southern lights, those gorgeous displays of shimmering colors that dance across the polar skies. They're caused by charged particles from the sun, carried by the solar wind. getting funneled down Earth's magnetic field lines into the polar regions, where they collide with atmospheric gases and make them glow. Jupiter has auroras too, but they're on a completely different scale. Jupiter's auroras are permanent features, constantly active, far more powerful than anything Earth produces. They emit more energy than Earth receives from the Sun in total. They're driven not just by the solar wind, but also by Jupiter's own rotation and by material ejected from its moon Io's volcanoes. Yes, you read that right. Io, one of Jupiter's moons, is the most volcanically active body in the solar system, and it spews out tons of material every second that gets ionized and swept up by Jupiter's magnetic field. This ionized material from Io forms a donut-shaped cloud around Jupiter called the Io plasma torus. As Jupiter rotates, its magnetic field drags this plasma around, creating enormous electric currents. Some of this plasma gets accelerated and funneled down the magnetic field lines toward Jupiter's poles, where it crashes into the atmosphere and creates those spectacular auroras. Juno flew directly over Jupiter's polar regions, something no previous mission had done, and its instruments captured the auroras in unprecedented detail. The images and data revealed structures that scientists had never seen before. There were discrete spots of intense aurora emission, bright patches that appeared and disappeared on timescales of minutes. There were swirling curtains of light, twisting and morphing as the magnetic field lines writhed in response to changing conditions in the magnetosphere. What really surprised scientists was the energy of the particles creating these auroras. On Earth, aurora particles typically have energies measured in thousands of electron volts. On Jupiter, some aurora particles were carrying millions of electron volts, making them far more energetic than anything in Earth's system. These particles were slamming into Jupiter's atmosphere with such tremendous force that they could penetrate much deeper than Earth's aurora particles, creating emissions at altitudes that would be impossible in our planet's auroras. The question then became, what's accelerating these particles to such high energies? The answer, scientists think, involves Jupiter's rapidly rotating magnetic field and the complex interactions between that field and the plasma environment surrounding the planet. As the magnetic field rotates, it can act like a massive particle accelerator, whipping charged particles to incredible speeds before flinging them down into the atmosphere. It's similar to how human-built particle accelerators work, except Jupiter's version is the size of a planet and operates continuously, powered by the planet's rotation and its interactions with its moons. But Juno's aurora observations revealed something even more intriguing. The spacecraft detected what scientists call dawn storms, massive bursts of aurora activity that occurred preferentially in the dawn sector of Jupiter's magnetosphere. These storms could brighten Jupiter's auroras by factors of 10 or more, creating brilliant displays that persisted for hours before fading away. What causes these dawn storms? Scientists aren't entirely sure yet, but the leading theory involves the interaction between Jupiter's rotating magnetic field and the solar wind. As material flows past Jupiter on the night side, it gets stretched out into a long magnetic tail, similar to Earth's magnetotail, but vastly larger. Periodically, this tail becomes unstable and releases bursts of energy, accelerating plasma toward the planet. When this happens in the dawn sector, you get these spectacular aurora intensifications. The more Juno observed, the more it became clear that Jupiter's magnetosphere, that vast region of space dominated by the planet's magnetic field, is one of the most dynamic and energetic environments in the solar system. It's not a static structure. It breathes, pulses, and erupts with activity, driven by the complex interplay between Jupiter's rotation, its magnetic field, the solar wind, and material from its moons. And speaking of Jupiter's moons, we can't talk about the planet without addressing the incredible retinue of satellites that orbit it. Jupiter has at least 95 known moons, ranging from tiny captured asteroids just a few miles across to the 4 massive Galilean moons, Io, Europa, Ganymede, and Callisto, each a fascinating world in its own right. While Juno's primary mission focused on Jupiter itself, the spacecraft's observations have implications for understanding these moons too. Jupiter's powerful magnetic field and intense radiation environment affect the moons constantly. Charged particles slam into their surfaces, alter their chemistry, sputter away material into space. For moons like Europa, which likely has a subsurface ocean beneath its icy shell, this radiation bombardment could be creating interesting chemistry in the ice, possibly even organic molecules. Europa deserves special mention because it's become one of the most exciting targets in the search for life beyond Earth. The moon is slightly smaller than Earth's moon, and its surface is covered in water ice, crisscrossed with dark reddish-brown streaks and cracks. Beneath that ice, scientists are confident there's a global ocean of liquid water, kept warm by tidal heating as Europa gets squeezed and stretched by Jupiter's immense gravity during its orbit. Juno's observations of Jupiter's magnetic field helped refine our understanding of Europa's ocean. You see, if Europa has a salty ocean beneath its ice, that ocean should be electrically conductive. As Europa orbits through Jupiter's magnetic field, the field should induce electric currents in that conductive ocean, which in turn would create a secondary magnetic field around Europa. Juno's sensitive magnetometer detected hints of exactly this kind of induced field, providing additional evidence for Europa's subsurface ocean. This ocean is a big deal, because where there's liquid water, there's potential for life. Europa's ocean likely contains more water than all of Earth's oceans combined. It's been liquid for billions of years. And there might be chemical energy available at the ocean floor, where the water meets Europa's rocky interior, similar to the hydrothermal vent environments on Earth, where life thrives in total darkness, independent of sunlight. NASA is planning a dedicated mission to Europa, called Europa Clipper, set to launch in the coming years, that will fly by the moon dozens of times and study it in exquisite detail. But Juno's observations of Jupiter's magnetic field and radiation environment are already helping scientists plan that mission, identifying the safest trajectories and the most scientifically valuable targets for Europa Clipper's instruments. Then there's Ganymede, the largest moon in the solar system, bigger even than the planet Mercury. Ganymede is the only moon known to have its own magnetic field, a feature it shares with planets, but no other satellite. This magnetic field creates a mini magnetosphere around Ganymede, a protective bubble that shields parts of the moon's surface from Jupiter's intense radiation. Juno's observations have helped scientists understand how Ganymede's magnetosphere interacts with Jupiter's much larger magnetosphere, creating complex magnetic structures and particle dynamics. Io, meanwhile, is a hellscape of volcanic activity, with hundreds of active volcanoes constantly resurfacing the moon. The tidal forces from Jupiter are so strong that they literally melt Io's interior, creating vast chambers of molten rock that erupt through the surface in spectacular plumes that can reach hundreds of miles into space. This volcanic activity makes Io the most geologically active body in the solar system, and it's the primary source of material for Jupiter's plasma torus and auroras. Callisto, the outermost Galilean moon, is the most heavily cratered object in the solar system, its ancient surface recording billions of years of impacts. Unlike its siblings, Callisto appears to be geologically dead, a quiet world that hasn't experienced the intense tidal heating that affects the inner moons. But even Callisto likely has a subsurface ocean, detected through similar magnetic induction techniques that revealed Europa's ocean. The discoveries from Juno have fundamentally transformed how scientists think about Jupiter and its entire system. It's no longer just the big planet with the cool stripes. It's a complex, dynamic, interconnected system where the planet, its moons, its magnetic field, and its radiation environment all interact in intricate ways. Every component affects every other component, creating feedback loops and cascading effects that scientists are still working to untangle. But perhaps the most profound implication of Juno's discoveries relates to how we think about planetary formation and evolution throughout the universe. Jupiter didn't just pop into existence in its current form. It has a history, a story that stretches back to the earliest days of the solar system and includes dramatic events like that core-shattering collision we talked about earlier. The prevailing theory of Jupiter's formation goes something like this. In the protoplanetary disk surrounding the young sun, solid particles began to stick together through a process called accretion. Near Jupiter's orbit, where temperatures were cold enough for water to freeze, these particles included lots of ice, making them particularly abundant. Over time, they accumulated into larger and larger bodies, eventually forming a solid core, perhaps 10 to 20 times Earth's mass. This core was the seed around which Jupiter grew. Once it reached a critical mass threshold, its gravity became strong enough to start pulling in the surrounding hydrogen and helium gas from the protoplanetary disk. This process accelerated rapidly, with Jupiter ballooning in size as it sucked in more and more gas. Within a few million years, it had accumulated most of its current mass, becoming the dominant gravitational force in the outer solar system. But then something happened. Maybe it was that massive collision we discussed, or maybe it was a series of smaller impacts. Or perhaps Jupiter's migration through the early solar system, moving inward toward the Sun before eventually settling into its current orbit, caused gravitational disruptions that affected its internal structure. Whatever the specific sequence of events, the end result was a planet with a diluted core, deep weather systems, and an asymmetric magnetic field. This history matters because it helps us understand exoplanets. When we discover a gas giant orbiting another star, we're seeing a snapshot of that planet at a particular moment in time. But what came before? What violent events shaped that planet's interior? What collisions, migrations, and interactions with other bodies left their marks? Juno's revelations about Jupiter suggest that every gas giant likely has its own unique story, its own scars from a violent past. Some exoplanets are even more extreme than Jupiter. There are hot Jupiters, gas giants, that orbit extremely close to their parent stars, completing an orbit in just a few days. These planets shouldn't exist according to traditional planet formation theories. Gas giants are supposed to form far from their stars, where it's cold enough for ice to exist. So how did hot Jupiters end up so close in? The answer is planetary migration. These planets formed farther out and then spiraled inward, either through interactions with the protoplanetary disk or through gravitational encounters with other planets. Some may have had violent, chaotic histories involving planet-planet scattering, where multiple giant planets formed in the same system and their mutual gravitational interactions flung some inward and ejected others into interstellar space. Understanding Jupiter helps us understand these exotic worlds. If Jupiter's interior is so complex, despite the planet forming in a relatively stable part of the solar system, imagine how much more complicated a hot Jupiter's interior might be, having experienced the extreme temperatures and tidal forces of a close-in orbit. These planets might have completely different internal structures, different core configurations, different atmospheric dynamics driven by the intense stellar radiation they receive. There are also super-Jupiters, gas giants several times more massive than Jupiter, and sub-Neptunes, planets somewhere between Earth and Neptune in size, that we don't have an example of in our own solar system. Each of these planet types represents a different outcome of the planet formation process, and studying Jupiter gives us a foundation for understanding how these diverse worlds might work. But let's bring it back to what Juno found, because there are still more surprises to discuss. One of the most unexpected discoveries involved Jupiter's gravity field and what it revealed about the planet's zonal winds, those jet streams that create the banded appearance we observe from Earth. Scientists had always wondered how deep these winds extend into the planet. Are they shallow features confined to the upper atmosphere, or do they penetrate deep into Jupiter's interior? The question is important because it tells us about how energy and momentum are transported through the planet, which in turn affects everything from the atmospheric dynamics to the interior structure. Juno's precision gravity measurements provided the answer, and it was surprising. The winds extend roughly 2,000 miles deep, about 3% of Jupiter's radius. Below that depth, the increasing pressure and density cause the interior to rotate more uniformly, like a solid body. But in that upper layer, different latitude bands rotate at different speeds, with the equatorial regions racing ahead of the polar regions. This creates enormous wind shear, the technical term for when adjacent layers of fluid move at different speeds. And when you have wind shear on the scale of thousands of miles and involving wind speed differences of hundreds of miles per hour, you get turbulence. Lots of turbulence. The boundary between the zonal wind layer and the uniformly rotating interior must be incredibly chaotic, with eddies and vortices constantly forming and dissipating as energy cascades from larger to smaller scales. Think about the amount of energy involved here. Jupiter's zonal winds represent the movement of enormous masses of hydrogen and helium, stretching thousands of miles deep and extending around the entire planet at each latitude. The kinetic energy stored in these winds is staggering, far exceeding the total energy content of all of Earth's atmosphere. And all that energy is constantly being replenished by heat from below and solar heating from above, maintaining these powerful jet streams over billions of years. The discovery of how deep the winds extend also helped explain another puzzle: Jupiter's odd gravitational field. When Juno measured the planet's gravity with such precision, it detected asymmetries that couldn't be explained by the planet's overall shape or by simple models of its interior. The data suggested that mass was distributed unevenly at different latitudes, and the culprit turned out to be those deep zonal winds. The winds transport mass around the planet, creating regions where there's slightly more or less material than average. This redistribution of mass creates tiny variations in the gravitational field that Juno was sensitive enough to detect. It's a beautiful example of how different observations connect together. The gravity data revealed the wind structure, which helped explain the magnetic field asymmetries, which in turn related to the disrupted core structure. Everything connects. Juno has also been monitoring Jupiter's Great Red Spot, that iconic anticyclonic storm that's been raging for at least 300 years, and possibly much longer. The storm is enormous, currently about 10,000 miles across, roughly the diameter of Earth, though it's been shrinking over the past century and a half. Historical observations show it was much larger in the late 1800s, perhaps twice its current size. Why is the Great Red Spot shrinking? Nobody knows for sure. Some scientists think it might be related to changes in the surrounding jet streams or variations in the amount of smaller storms that the Great Red Spot consumes. The storm feeds on smaller vortices, absorbing them and gaining their energy and momentum. If fewer small storms are available to feed it, the Great Red Spot might gradually starve and shrink. But here's what Juno discovered. The Great Red Spot extends deep, just like the other atmospheric features we've discussed. Juno's microwave radiometer peered beneath the visible cloud tops and found that the storm has roots extending hundreds of miles down into Jupiter's atmosphere. It's not a shallow surface feature. It's a three-dimensional structure, a vast column of rotating gas that extends through multiple atmospheric layers. The storm's depth helps explain its longevity. Shallow atmospheric features dissipate quickly because friction with surrounding layers saps their energy. But if a storm extends deep enough, it can tap into energy sources in the lower atmosphere, sustaining itself indefinitely. The Great Red Spot has found a stable configuration, a balance between energy input from below and energy loss through friction and radiation, allowing it to persist for centuries or possibly millennia. Juno's close-up images of the Great Red Spot revealed exquisite detail in the storm's structure. There are complex swirls and eddies within the larger vortex, regions where material is being drawn into the storm and other areas where it's being ejected. The cloud tops show intricate patterns of light and dark material, reflecting different chemical compositions and temperatures. It's a dynamic, evolving system, constantly churning and mixing the atmosphere. But the Great Red Spot isn't alone. Jupiter hosts numerous other storms and vortices, including several other long-lived features like Oval BA, a smaller reddish storm that formed from the merger of three white ovals in the late 1990s. These storms interact with each other, sometimes merging, sometimes being torn apart by the powerful jet streams. It's a constant battle for survival in Jupiter's violent atmosphere. One of the things Juno's long mission duration has allowed scientists to do is monitor how these storms change over time. By repeatedly imaging the same features from different angles and at different times, they can track the evolution of individual storms, measure wind speeds, and observe how storms interact with their surroundings. This kind of long-term monitoring is invaluable for understanding the underlying physics that governs Jupiter's atmosphere. And then there are the lightning storms. Jupiter has lightning, lots of it, though it's different from Earth's lightning in interesting ways. On Earth, lightning typically occurs in thunderstorms driven by water vapor rising and condensing, creating charge separation that eventually discharges as a lightning bolt. On Jupiter, the situation is more complex. Juno carries a radio and plasma wave instrument that can detect the electromagnetic signals from lightning strikes. What it found was fascinating. Jupiter's lightning occurs mostly near the poles, unlike Earth where lightning is most common in the tropics. The lightning is also more powerful than Earth's, with individual bolts carrying enormous currents. Some of Jupiter's lightning strikes are so energetic they can be detected from millions of miles away. The distribution of lightning tells us something about where convection is most active in Jupiter's atmosphere. The poles apparently have strong rising columns of gas, probably driven by that internal heat we discussed earlier. These rising columns lift water vapor and other materials to higher altitudes where clouds form and lightning is generated. It's another piece of evidence that Jupiter's atmospheric dynamics are fundamentally driven by heat from below, rather than just solar heating from above. Now, as Juno continues its extended mission, orbiting Jupiter again and again, the spacecraft itself is gradually succumbing to the harsh radiation environment. The electronics are being degraded by the constant bombardment of high-energy particles. The solar panels, which provide power for the spacecraft, are slowly darkening as radiation damage accumulates. Eventually, Juno will fail, either suddenly, when a critical system stops working, or gradually, as its power output declines below the level needed to operate the instruments. When that day comes, mission controllers will deliberately crash Juno into Jupiter's atmosphere, ensuring the spacecraft doesn't accidentally contaminate any of Jupiter's moons with microbes from Earth. It's a necessary precaution because some of those moons, particularly Europa, might harbor their own life forms, and we can't risk introducing Earth organisms that could disrupt or destroy potential alien ecosystems. But before Juno's mission ends, it has already secured its place in history as one of the most successful planetary exploration missions ever flown. The spacecraft has fundamentally changed our understanding of Jupiter, revealing a world far more complex and dynamic than anyone imagined. It showed us that Jupiter isn't a simple ball of gas, but an active, evolving planet with weather systems that extend thousands of miles deep, a disrupted core that tells a story of ancient violence, and a magnetic field that reflects the exotic physics happening in its interior. Every discovery raised new questions. If Jupiter's core was disrupted by a massive collision, when exactly did that happen? What was the impactor? Where did it come from? How do those deep atmospheric structures interact with the interior? What processes maintain those bizarre polar cyclones in their geometric arrangements? How does Jupiter's magnetic field change over time? What's really happening in that zone of metallic hydrogen, where the magnetic field is generated? These questions will drive future missions and future research. Scientists are already planning the next generation of Jupiter exploration, missions that might use new technologies to probe even deeper into the atmosphere or study the planet's moons in greater detail. Each mission builds on what came before, adding new pieces to the puzzle. And that's the beauty of scientific exploration. We never really finish. Every answer generates new questions. Every discovery opens up new avenues of investigation. Jupiter, despite being studied for thousands of years, despite having multiple spacecraft fly past or orbit it, despite all the observations from Earth-based telescopes and space telescopes, it still has secrets to reveal, still has surprises waiting for us. The universe is vast and full of wonders, and Jupiter is just one planet orbiting one star in one galaxy among billions. But by understanding Jupiter, by peeling back its layers and exposing its inner workings, we gain insights that apply far beyond our solar system. We learn about how planets form, how they evolve, how their interiors behave under extreme conditions. We discover new physics, new chemistry, new processes that expand our understanding of what's possible in nature. And sometimes, just sometimes, we find something inside Jupiter that nobody saw coming. A disrupted core, weather thousands of miles deep, an asymmetric magnetic field, diamond rain, geometric arrangements of polar cyclones. Things that challenge our assumptions and force us to think differently about these giant worlds. That's what makes exploration worthwhile. Not just the answers we find, but the questions we never thought to ask. Not just confirming what we expected, but being surprised by what nature actually did. Jupiter has been surprising us for thousands of years, and if Juno's discoveries are any indication, it will continue surprising us for thousands more. The gas giant that's been our companion in the solar system, the planet that protected Earth from asteroid impacts, the world that fascinated ancient astronomers and continues to captivate modern scientists, turned out to be hiding extraordinary secrets in its depths, and we're only just beginning to understand what they mean.